Okay, so here's example number 6, and with example number 6 we need to work out some information regarding nuclear fission of uranium-235. So when we're looking at example 6, one thing to be aware of here is these particles that we're given here, we're given the masses of them, but each of these particles, like the uranium-235 here, this is the mass of the atom, not the nucleus, and really we want the nuclear mass, not the atomic mass. Okay, so to get the nuclear mass we would need to take 92, the mass of 92 electrons from this number here, okay? But actually in this question you don't really need to do that, because you've got 92 electrons on this side, you've got 56 and 36 on this side. The barium has 56 electrons and the krypton has 36. 56 and 36 makes 92. So because you've got 92 electrons on both sides, it doesn't actually matter, because if you take the mass of 92 electrons from this side, you're also going to take the mass of 92 electrons from that side to calculate the nuclear mass of these things. So actually it makes no difference, because you're just doing the same thing to both sides. But it's just something to be aware of, that these actually are the masses of the atoms, not the nuclei. Okay, and I'll show you later on in this video that you can take off the mass of the electrons so that we're working with nuclei then, but it actually makes no difference to your calculation. Okay, so first of all you're asked to calculate the total mass of the original isotope of uranium plus the neutron. So to do that, uranium mass is 235.043923, and you're going to add on to that the mass of one neutron. Okay, and that gives you an answer of, if you work that out, 236.052588U. Okay, now for B, you've got to calculate the mass of the products. So the mass of the products is the mass of barium, and make sure you get the right one, it's 143.922941, plus the mass of krypton, 89, which is this one, 88.917636, plus the mass of 3 neutrons. Okay, now if you work that out, you get this, 143.922941 plus 88.917636 plus 3 times 1.008665 gives you 235.866572U. Okay. Now part C says calculate the change in mass. So you can see the mass of the products is less than the mass of the original reactants, so to speak. So the change in mass, or delta M, is equal to 236.052588 minus 235.866572. Okay, so that's going to be 236.052588 minus the original answer, and that gives you 0.186016U. Okay, so that's the difference in mass between these two things. So these products here have that much less mass than the original reactants. Okay, now it asks you, does this energy represent energy gained or lost by the system? Well, as we go from here to here, energy is lost. Okay, energy is lost from the nuclei, but kinetic energy is gained then by the reactants, by the product, sorry. Kinetic energy is gained by the product. So you could say this is energy lost from the nucleus, but it's then released as the kinetic energy of the products. Right, so D now asks you to convert the mass change into energy released in the fission event. So the energy released is just equal to this mass, 0.186016U, multiplied by 931.5, because that's the number of mega electron volts in 1U. And that gives us 173.273904 MeV. Okay, and you could round that to 173.27 MeV, let's say. Okay, so that's the amount of energy released when this nuclear fission event occurs, because these products have a higher binding energy per nucleon than the uranium did, and therefore the nucleons are more tightly bound. They're in a lower potential energy state, so they must release energy, and that's the amount of energy that's released. So when we go from here to here, energy is released. Right, so what I'm going to do now is just show you that actually taking the electrons off here makes no difference. So let's look at the mass of the reactants here. Okay, so the mass of the reactants here is going to be the mass of the uranium atom. Okay, so 235.043923. And we're going to take away from that the mass of 92 electrons. Now, if you remember, the electron mass is equal to 0.00055 U. Okay, so 92 times by that. Now that's going to give us the nuclear mass of uranium rather than the atomic mass, okay, because that's the atomic mass. Take away the electrons, that gives us the nuclear mass, okay. So that's the mass of this, or the nucleus of this to begin with, and then we're going to add on the mass of the neutron as well, 1.008665. So that's our mass of our reactants. The mass of the products, okay, is going to be the mass of the barium, which is 143.922941. That is right, isn't it? Yep. And you're going to take away from that the mass of 56 electrons. Okay, and then you're going to add on to that the mass of the krypton atom, take away the electrons. So the krypton atom, the mass of that is 88.917636. Okay, minus the mass of the 36 electrons. Okay, so if I just move this out of the way a little bit, so that's the mass of your barium nucleus, krypton nucleus, and then obviously we'd have to add on the mass of 3 times by the neutron mass, okay? And let's just get that out of the way there. So that's going to give us the mass here of that. So let's work this out. So the mass of the reactants okay, so that's going to give us 236.001988 U. Okay, the mass of the the products then, sorry, is whoops. Right, plus 0.7636. Okay, plus 3 times the mass of the neutron, so that's 235.815.972. Okay, so we can now work out the mass defect, and we just take that and minus this from it. Okay, so it's going to be 236.001988 minus 5.815.972. Okay, so 236.001988 minus that, and that's going to give us an answer of 0.186 U, which, if I'm not mistaken, is exactly the same mass defect as we had when we did it without taking away the electron masses. Okay, so you can see it does make no difference.